So far we have discussed discrete time Markov chain and then corresponding continuous time Markov chain. So, we have seen how the guiding formulas, the characteristic of a Markov chain, the corresponding rate matrix, all those things we have already discussed. Now, what we will do is we will see the application of this continuous time Markov chain for our case, that is the trunk switch analysis. That is where we started this detour of queuing analysis. So, now we are in a position to launch to that aspect. So, there two important formulas are very important, which are called Erlang formulas, Erlang B and C formula actually. So, we will see how to derive that, but before that in this lecture particularly we will initiate the whole process and we will discuss some very famous queuing model or very elementary queuing model we should say, that is called the MM1 queue. So, let us try to understand first of all this notation. When we say this MM1 queue, what do we mean by this notation? So, let us try to understand this. This is actually according to Kindle's notation. Okay. So, what is Kindle's notation? Let us try to understand. It is actually with slash, there are 5 spaces. This is 1, 2, 3, 4, 5 actually. Okay. So, there are 5 spaces. Over here you can see 3 I have populated, we will come to that why 3 has been populated. Okay. So, the first space actually, so this is actually a typical queuing system analysis. Okay. So, for the queuing we know that the arrival process is very important and the service process is very important. These are the two things which has to be specified. So, the first basically first location specifies what is the characteristics of an arrival process for which we are doing analysis. Okay. So, this is arrival process. If we say M over there, so if we write M in the first place, that means the arrival process is Markovian with, of course, there will be some arrival rate that will be specified. If it is Markovian, that means it has to be Poisson. So, it must have a associated rate which is lambda. Okay. And we already know that it is a homogeneous system and it is a stationary system, for that only we are trying to analyze. Okay. So, this is the first thing that has to be specified. So, if I say M, it is Markovian, if I say D, that means it is deterministic. So, that means it is a regular interval with some arrival interval, okay, some specified arrival interval. If I say G, that means it is generalized. So, it can take any distribution. Okay. So, accordingly, so right now we are concentrated on Markovian because we know that we want to do trunk switch analysis where the call arrivals are generally following Poisson process with some arrival rate lambda. So, it is always Markovian. So, we can write it Markovian. Second place talks about the service process. Okay. So, again we have a Markovian service process. So, again we can write M. There also we can have other options like deterministic, generalized, any distribution you can take, Weibull, Gaussian, whatever comes to your mind. So, all kinds of things we can take, any distribution, it can be even deterministic also, but for our case already call durations are again Poisson distributed or sorry exponentially distributed with rate mu. So, we will take that. Okay. The third place, so basically this is arrival process, this is service process. What is the third one? So, the third one gives a number. Okay. I can put some small m. Okay. This gives a number, and what this characterizes, now we have characterized arrival and service process. Now, we have to characterize that how many servers are there. Okay. So, this specifies the number of servers. Okay. The fourth place tells me, so basically now what has happened for a particular queue, I have a queue, followed by a server or a server system, multiple servers also can be there. I have arrival with some distribution. I also have, for each packet there is a service. So, service has some distribution. Okay. I have now defined how many servers are there. So, this is m 1, 2 up to m servers are there. Okay. But I still have not decided in the queue how many places are there, how many customers or how many packets I can keep them. So, what is my buffer size? Okay. So, that is what is defined over here, but remember when I define this, this is actually tells me that how many customers. So, maximum number of maximum number of packets that can be accommodated in the system, very important. So, it talks about overall in the system how many packets or how many customers I can accommodate maximum. So, if Q has a length of k, then how many total customers I can accommodate. So, k can wait over here and m can be served. So, this should be m plus k. So, if I specify a number capital K, that capital K must be small k, which is this, the number of buffer place plus m number of servers. So, this specifies in the system at max how many customers I can hold. The last one gives me another interesting things. This probably we will not be mostly taking into account. This says how many customers from outside are making arrivals. This is something we have never talked about. This is a finite customers system. If we specify that number, if we do not specify, it is infinite. So, generally our assumption will be infinite customers. So, outside the queue who are making arrival, how many potential customers are there who will be making arrival. So, suppose I talk about a particular railway counter, okay, railway ticket booking counter. Okay. So, in that railway ticket booking counter, how many customer potentially, that means the overall population of the area who will be making potential arrival to this railway booking center. Okay. If that I can approximate or assume to be infinite, then that is infinite. Okay. General assumption will be infinite. But I can also have a finite population over there. Okay. So, I can say that some n number of customers are there outside the system who can potentially make arrival to this particular system, this particular queuing system. Okay. So, if they are not specified otherwise, then the value can be taken to be infinity, okay, especially these last two. So, if I do not specify over here MM1 queue, so that means the arrival process is Markovian, service process is Markovian, only one server is there. So, it is a single server queue, and then the last two things are not specified, that means I can take potentially there to be infinity. So, that means there is no restriction in the buffer, I can have infinite buffer. So, it is an infinite buffer single server case. So, whenever I say MM1 queue, it is actually infinite buffer single server case. Okay. So, that is what we are describing over here. So, this is the system we want to analyze. That means, there is only a single server and there are infinite buffer, customers are arriving with Poisson distribution with a arrival rate lambda and being served with independent exponential distribution with rate mu. This is what is happening in the system. I want to analyze this system. I want to see what will be the corresponding average number of customers, the average delay that it gets. So, all those things, distribution of all those key parameters. So, how do I see all those things, how do we do analysis applying Markov chain, that is our target. Okay. So, let us now try to see, because everything is Markovian. So, what can be the state description now? The state description, as we have already so far discussed, that it can be, because all are Markovian. So, I can just describe the states by number of customers in the system. So, that is countable. So, the state is defined by only one value 0, 1, 2. Now, you can see how far this state can go, because the queue length is not finite. So, basically state also potentially can grow up to infinity, because as many customers, if the too many customers are coming and the server is not capable of serving all of them. So, it will just go towards infinity. So, therefore, potential state can go up to infinity. If my server was having finite, then this potential state will go up to, sorry, not server, my amount of customers who can be kept in the system, that was finite, then the state will go up to that finite number only. So, accordingly your Markov chain will be either infinite or finite. So, it depends on what description we are giving. So, if there is a finite number in the fourth column or fourth place, then always it will be a finite Markov chain. If I do not have any specification, that means it must be infinity, like for MM1 queue. So, it is infinity. So, therefore, it goes to infinity and it is an infinite dimension, means infinite Markov chain. Okay. So, now graphically I can represent. So, you remember we had this rate, and due to non-simultaneity principle, it can only go in the next state and it can come back to the next previous state only. So, there will be arrows over here, that is the transition, rate transition matrix. So, if you have some n, sorry, n minus 1, n plus 1, so, from every state it can grow to next state, and from every state it can come back to the immediate previous state. That is the overall Markov chain. Okay. Now, the rate matrix, what should be the associated rate? This will be, we have already seen, this will be with arrival rate. So, if that is lambda, so always it will be lambda, and this is with service rate. So, always this is mu. Okay. Now, can I draw, means I have drawn the Markov chain, can I now put the set of equations? Okay. I can do in one way, which is actually by writing pi q equals to 0, and then q matrix will be with this lambda mu, you will be able to populate the way we have discussed. It will be an infinite dimensional matrix. Forget about the diagonal term, you put the off diagonal term, one on this side it will be all lambda, one on this side will be all mu, and then this will be minus lambda plus mu. We have already seen that. So, and all rest of the things will be all 0. Okay. And then put all the set of linear equation. This is one way of doing it. Other way we have discussed that total outgoing rate, because it is stationary. So, that means total outgoing rate of probability should be balanced. So, incoming should be balanced with outgoing. So, if this has a probability of pi 0, this has a probability of pi 1, this has a probability of pi 2, then lambda pi 0 must be equal to mu into pi 1, because that is the rate into associated probability, that is the rate of probability that will be coming in, and rate into associated probability. So, rate is lambda and associated probability is pi 0, that should be going out, this should be balanced. Similarly, if I construct a system over here with a combined system state of 0 and 1, what is the outgoing rate? So, that should be this one, and what is the incoming rate? That should be this one. So, again I can put lambda into pi 1 must be equal to mu into pi 2, and so on. Okay. So, lambda into pi, let us say n minus 1 must be equal to mu into pi n. Like this you will be able to put means series of equation. Now, from here I can see the relationship pi 1 must be equal to So, lambda by mu pi 0. Let us call this lambda by mu, you will see this is a very important thing, that is rho. Okay. So, let us talk about that part. Now, over here we need to also characterize something, okay. That is called the stability condition. We have already told stationary. So, but there is a condition that it will remain stationary. Very generally think about it, a particular queue is there, okay, and a single server is there. Server is serving at a rate mu, arrival is happening at a rate lambda. If somehow this arrival rate lambda, if it is greater than mu, then what will happen? So, that means the rate at which it is arriving, he is not able to handle that, because he is serving at a lower rate. So, the queue will keep on building up, and what will happen? It will remain in transient, it will never reach steady state, it will go up to infinity, because queue will always build up, because he is not able to handle the incoming rate. So, therefore, queue will always build up. So, stability condition is the reverse of that it must be less than, okay. Even equal also will later on see that equal also will not hold, there also queue will not become stable. Okay. So, for stability condition what we need is this lambda must be less than mu. Okay. This is one condition that has to be true. Okay. That is something which has to be true if I have to do a steady state analysis. If this equation to be true, then this condition must be satisfied, that our arrival rate must be less than the service rate. Otherwise, there is no, actually the queue will not give me any satisfactory answer, it will always go up to infinity, the delays will go to infinity eventually, and it will never reach steady state. Okay. So, this will always happen. So, at least that condition has to be satisfied. What does that mean? This condition, this rho less than 1 must be always satisfied, because lambda is less than mu. So, therefore, lambda by mu must be less than 1. So, this condition has to be true. So, over here if I just replace by this definition of lambda by mu. So, I can write from here pi 1 is equals to rho into pi 0. Similarly, from here what do we get? Pi 2 equals to some rho into pi 1. Now, I can replace this definition of pi 1. So, basically it becomes rho square pi 0. Similarly, it happens. So, finally, this pi n minus 1 will be rho to the power n minus 1 into pi 0, and pi n in general will be rho to the power n pi 0. So, this sets of equation we know. Rho is something which is the characteristics of the traffic, I must be knowing that, because if I do not know the characteristics of the traffic, that what is the arrival rate, what is the amount of service it is bringing average on an average, if I do not know that, then there is no point in characterizing this whole thing. Okay. So, that rho must be known, and rho is actually this lambda by mu, this is told to be the amount of service that a particular input or arriving traffic is bringing in. Let us try to understand this part a little bit more carefully. So, what we are saying, what is lambda? Lambda is average number of arrival per unit time, we know that number of, because it is the rate, number of arrival per unit time. So, basically if you talk about unit time as 1 second, so 1 second lambda number of arrival will be happening. What is mu? Mu is the service rate. We also know what is the definition of 1 by mu, that is the, according to the Poisson, this one, this is the average service time. Okay. So, lambda number of average arrival are occurring, if I serve them, the average service time is 1 by mu. So, on an average how much time per unit time, if I can serve all of them. So, suppose some of them are arriving, I am actually putting them one after another. So, it just says that if I take the average these things multiplied by lambda, that is within unit time, what is the fraction of time being occupied, as you can see. Okay. So, average fraction of time that is being occupied. So, that is why, because rho is 1 less than 1, generally if rho is greater than 1, then it will be more than 1 basically. The fraction of time it requires from the system or from the server, it will be actually greater than 1, that is not possible, server will not be able to handle, that is why the queue keep on growing. Okay. So, it will be something like this, the situation will be that there are multiple arrivals. So, you are trying to accommodate them, but by that time some more arrivals are happening. So, you are not capable of handle all of them. Okay. So, it will always be difficult to handle all these things, because the arrivals are happening too fast. Whereas, if you do arrival which is below the service, then there will be some gaps in between. Okay. So, rho actually characterizes the amount of time out of that unit time, okay, or if you take a very long this one, what is the fraction of time that the server is getting occupied. That means, this is the amount of service that is brought in for the server. You remember for Lee's graph also we discussed about that, how much amount of time the server will be occupied, or a particular this things switch port will be occupied. Okay. So, that is actually rho, and this is characterized as the amount of traffic, and the unit is Erlang. Okay. So, basically when I say 1 Erlang traffic, that means the server will be completely occupied. The amount of traffic that is being brought in, or it means actually 1 Erlang means lambda is equal to mu. Okay. So, the server targeted server will be completely occupied if I say 1 Erlang. If I say 0.5 Erlang, that means server will be 50% occupied. So, that is the basic definition of rho. Okay. So, once we have defined this rho, now can I just try to see how do we solve this equation in a recursive manner. So, first thing we will have to solve, as you can see each of them are getting linked to this pi 0. So, therefore, I have to first solve pi 0, because everybody is means defined with respect to pi 0. So, everybody will be defined if I can define the pi 0. Okay. How do I define pi 0 now? I have another equation left. I have always talked about that equation, which is the normalization equation. So, summation of pi I going from 0 to infinity, because there are infinite state and state starts from 0, this is equal to 1, this is something I know. If I put all those pi I over here, then I will be probably getting my pi 0 solution, because that is the only unknown which will be remaining. So, let us try to do that. So, basically this will be pi 0 plus rho into pi 1 rho into pi 0, that is pi 1 plus rho square into pi 2 and so on, right. This is equal to 1, or I can write summation I equal to 0 to infinity pi I can write rho to the power I pi 0 is equal to 1, or from here pi 0 goes out, because that does not depend on I. So, pi 0 will be equal to 1 by summation rho to the power I goes from 0 to infinity. This is the geometric series and rho is less than 1. This is something I know already. If that is the case, this is a geometric series, we know that its summation is 1 by 1 minus rho. So, therefore, this will be 1 by 1 minus rho, or this is 1 minus rho. So, pi 0 happens to be 1 minus rho. Again, rho is a given parameter. Okay. So, rho is something which is already given to me. Once I know this rho, I will be able to calculate pi 0. Once I know pi 0, now you can see all the pi n's are calculatable. So, basically what we can do now, so now I can define any pi n is equal to rho to the power n pi 0, which is nothing but rho to the power n 1 minus rho. I have solved the state equations and I have got the corresponding every state. So, I have got the analytical formula for this. So, this is the famous formula of MM1Q. So, in MM1Q the states are defined by this. as you can see, this is a very well known distribution, this is called geometric distribution. Again you can see a memoryless thing has been reproduced. So, this is a geometric distribution with parameter rho, right, and of course, it is a PMF because n values are discrete, it can take 0, 1, 2, 3 those values only. Okay. So, I have got the distribution of number of customers. Now, all we have to do is we have to take the average of this, average number of customers. Okay. So, how do I take average? I know the PMF is average only, I will have to take. So, n, or you can even write I pi I summation I equals to 0 to infinity, that should be my n bar. Okay. So, all we will have to do now, we have to calculate this summation. This is a very easy, means you have done that in your 12th standard math. So, this summation can be easily calculated, pi I just replace, that should be rho to the power I pi 0, and pi 0 you can put, or you can pi I you can put this rho to the power n 1 minus rho, you put that and then you do that summation and basic formula will come down to be. Okay. So, once I know n bar, it is very easy to calculate. I know average number of customers in the system. Now, how do I get the delay? You remember my delay was average number of customers divided by lambda, that is the Little's formula. So, I put the Little's formula, I get my delay also, average delay. So, average delay will be this n bar divided by lambda, which is rho 1 minus rho and divided by lambda. Now, rho is lambda by mu, divided by lambda, that should be, so this is rho. So, divided by lambda, that should becomes 1 by mu. So, I can write it 1 by mu, that is my average waiting time. Okay. So, as you can see, once I know the construction, how to construct a CTMC, from there I can easily analyze the average, the condition that we have talked about, the average waiting time. Okay. So, that is something we can calculate, average number of customers in the system or average number of packets in the system. If it is a MM1 queue which is characterizing the circuit switching or call switching, then I can see average number of calls, okay, that are waiting in the system, I can characterize that. Average amount of waiting time for each calls to be established, so that also I can characterize, that is W bar. So, these are the parameters we can characterize. We can also see the number of customers, their basically number of customers, their distribution, their PMF, that we can do. Even waiting time also we can calculate the associated distribution, that will be another exponentially distributed, but right now probably we will skip that because we are not trying to do the MM1 queue over here. So, what we will do with this background now, we can go ahead and do the derivation of other important trunk switching calculation. So, next class we will try to do that, we will try to see what is the system that is being associated with it and how do we analyze that system. Okay, thank you.